Welcome everyone to our 13th episode of our 13th class of our series Get Started in OpenSees with STKO. We already went through a lot of topics. Today we talk about material and geometrical nonlinearities and how to include them in your OpenSees models with STKO, of course. This is like the base that we want to use for next week's class, which is going to be about plasticity approaches, so distributed plasticity or lump plasticity approaches, but we need to have a nonlinear material and nonlinear geometry to be able to model these kind of approaches. So just moving forward, if my computer, we're going to talk about how to model nonlinear materials for concrete and steel and nonlinear geometry. So actually it's very basic what you actually do in OpenSees and STKO to do these couple of things. And it's more about constitutive model than actual programming or finite element modeling. But we have to go through this, otherwise we will not know how to move forward. And we're going to talk just about concrete and steel because I'm preparing documentation for our material specific for masonry. And so I didn't have the material yet to share with you, but I'm going to do an episode, a class just on masonry at the end of the series. So don't worry. We already talked about Uniaxial Materials, I think in week 4, when we discussed, in week 5, when we discussed physical properties. So what is a uniaxial material? It's an object that in OpenSees represents the relationship between two things. It can be stress and strain, it can be force and strain, it can be force displacement or moment rotation relationships. It depends on what you want to model. Today we're going to talk mostly about stress and strains or force and strain relationship, which are the ones that we mostly use for beam column elements. But this is just for you to recap that a uniaxial material is just a relationship between two things, is a function. So, and it's useful if you want to model something that it's in one plane, because if you are going forward for like modeling faces and so shells or plates, or if you want to model solid objects, you need to move on to other types of material that we do not cover in these classes. So how do you add nonlinearity to this kind of uniaxial material? The basic one, of course, is the elastic material. There's no nonlinearity. There's just a linear behavior. You define a stiffness, and that's it. There's not much more for you to do. You can define a different behavior in the positive and negative quadrant of the stress and strain relationship or force deformation relationship, but nothing really changes here. What changes is when you move on to some more different kind of curves. So if we're talking about concrete behavior, what we want to model first, of course, is the compressive behavior of concrete. And how do we start? We start with the most basic concrete that it's in OpenSees, which is concrete 01. What we can add in comparison to the linear behavior of the elastic material is we can add concrete maximum compressive strength. We can add a crushing strength and corresponding deformation, corresponding strains to both of these points in the curve. The concrete 01 does not see the presence of any tensile strength. So if you see the graph in the positive quadrant is flat here. And of course, parameters should be inputted as negative because we're talking about compression, and as a convention, compression is considered negative. But in this case, if you don't input them as negative, they will be automatically converted to negative internally. And how do you do that in STKO? This is like a few basic default values that you can have in Newton millimeters. So MPa and strains is adimensional. And you can see that when you test for a monotonic test, both in the positive, in the negative and the positive direction, we obtain exactly the same curve that concrete 01 describes in the OpenSees manual. If you then move on to a cyclic test, you can see that there is the possibility to model the unloading stiffness. So that there's a degraded linear unloading or reloading stiffness for this type of concrete. But of course, that's just in the compressive behavior. Then if we move on to the concrete 02, oh, sorry, guys, this should be a bit more visible. Yes, so concrete 02, instead, we can have linear tension softening added to our constitutive model. Yeah, okay, no problem. You can see. I just wanted to add here, I'm sorry, it's overlapped with the graph, a few of the Professor Scott's suggestions for these additional parameters, the default additional parameter for concrete 02. So if we are doing just a concrete 01, we already have maximum compressive strength, we have crushing strength and the corresponding strains, and we need to add the lambda, the tension strength, the tensile strength of concrete, and the tension softening stiffness in the absolute value. So how to do this? Yeah, this is what happened here. That was not working very well. Exactly. So we can add tensile strength as a percentages of compressive strength, has a base. We can compute the tension softening stiffness also as a percentage of the initial slope, half of the initial slope, and then we can use a lambda that's included in this range, and we will have, let's say, consistent behavior of concrete material. Of course, naturally here you don't see the scale, but this value is much lower than this one because we inputted tensile strength of 3 compared to a compressive strength of 25. So always remember that the scale of the material tester graph, it's based on the maximum values. So it's zoomed in what you can actually fit in the window. And so what we're doing here is we have these 2 additional parameters for linear tension softening, and this last one is actually giving us a ratio between the unloading slope at the ultimate strain and the initial slope. So what does this mean? I don't know if you guys remember now, we talked about how the unloading and reloading stiffness is degrading in the concrete 01, like this. For concrete 02, we can have a different kind of degradation, which actually kind of capture a bit better mathematically what's the behavior of concrete. So if we are just not putting any tensile strength here, for example, with Ft equal to 0, we will have a similar behavior in the cyclic loading and reloading cycle for just the compressive strength, which is much similar to the ones for concrete 01, but with this difference in the unloading and reloading stiffness. Or if we actually model the full capabilities of concrete 02, we can add this tensile strength. So I'm going to leave you guys all of this presentation as always, because you can always refer to these default parameters, input them in your material tester when you are adding a new material, and you can also use the same setup for the material tester, which some people always ask me, how do I set up the material test? Like this, you can actually see what's the curve supposed to look like and then play with the parameters and scale them to adapt them to your models. Going forward from concrete, we need to pass to steel. Of course, we need to model nonlinearity in steel. We start with kinematic hardening. To model kinematic hardening, we need to input both, of course, the initial stiffness, the yield strength, and ratio, that is our strain hardening ratio, that will allow our linear curve to bend and move forward infinitely in this case for steel 01. And the same is what we find in STKO when we model with these kind of parameters. And we have a cyclic behavior which does not degrade in this case. Just there's a degradation of the initial stiffness, but there's a degradation of the ultimate displacement because of the cycle, but there's not degradation of the slope. But then if we move forward to steel 02, which is a Giuffre-Menegotto-Pinto model with isotropic strain hardening also here, we have the addition of putting parameters that controls the transition from the elastic and the plastic branch. So after getting to the yielding point, we can have model the actual yielding, and this is governed by these 3 additional parameters, R0, CR1, and CR2. These are the default values that are suggested by the OpenSees documentation. you can actually see what changes if you play with them through the material tester in STKO. And of course, here we have an unloading and reloading branch, which model the same transition between the plastic and inelastic branch, also in the unloading and reloading. If we want to model something different, some type of material nonlinearity, which is not, let's say, codified specifically for steel or concrete, and we don't know very well what's the curve, but we know, let's say, a bit of the backbone of what it's supposed to look like and which are the points that it's supposed to touch, we can use the hysteretic material. The hysteretic material is really useful. It can be used to model masonry, to model shear, to model very different things. What you need to know is it's just a 3 points backbone function. So you define the coordinate of the backbone with the first parameters that are there. You can have 2 points or 3 points additionally, and you can have them both in the negative and in the positive quadrant. And also what you can add is pinching to model the opening and closing of cracks in a cyclic loading, and damage, both in terms of ductility and energy. So what you actually come up with is you don't have to input the stiffness. Stiffness is computed inside. And this stiffness is used to apply with a beta factor to the ductility in order to define the stiffness of the unloading branch. What we obtain here is, for example, if we want to model a simple shear cracking and then shear maximum strength, we can actually, this is actually done for a steel, but it's the same for any other type of nonlinearity that you want to model. You can see that we can obtain a cyclic loading and reloading behavior, which is highly nonlinear. So there's not just like we saw here, one type of nonlinearity, but there's additional ones. Then finally, moving on from the hysteretic material, if you need not 3 points, but 4 points in your backbone curve, we can use the pinching for material. So here you can add 3 types of cyclic strength and stiffness degradation: the unloading stiffness, the reloading stiffness, and the strength degradation. I'm sorry, there's been some problems with the formatting, moving on from one computer to the other today. I don't know why. Yes, so I'm sorry that you cannot see all the information. There you are. So in the pinching for material, we have a pinched for load deformation response and a degradation under cyclic loading. It's the same for our hysteretic material. We have 4 points to define our backbone, and we have them both in the positive quadrant and in the negative quadrant. When we want then to move forward to the unloading branch and reloading branch here, I only put the coordinates of the unloading branch because it was too crowded, the graph, but anyway, they are the same, exactly the same of the ones for the reloading branch. You see, we have 3 parameters. So starting from the bottom, let's say from this point of the unloading branch, we define this point, we define the y coordinate of this point has the U force P, U force N value. So the ratio of strength developed upon unloading from negative load to the minimum strength developed under monotonic loading, multiplied for the value of maximum strength that we reached in the negative quadrant. So it's like something that is scaled down from this point. Then if we move forward in the unloading branch, we need another point. This point is defined, x-axis is defined as the ratio of the deformation at which reloading occurs at the minimum historic deformation demand. So here, this is the minimum historic deformation demand that of course moved towards 0 as the cyclic moves along, multiplied by this minimum historic deformation, and has a y-axis. We have, this is also wrong. Yes. We have the ratio of the force at which reloading begins to force corresponding to the minimum historic deformation demand. So in terms of force, multiplied by this exact value. So what you understand is that here we can have an unloading and reloading behavior that moves towards 0. And this is allowed also by the pinching parameters too. So we don't have a specific pinching parameter here because pinching is already, let's say, included in the definition of these 3 additional parameters compared to the hysteretic material. This is a backbone that you can use, for example, for modeling masonry behavior or shear behavior of a concrete column, for example. So you have many different options to use if you want to model material nonlinearities. What I suggest is to always have your experimental results ready so that you can compare them to what the material tester is giving you and trying to obtain similar curves that actually describe how your model is going to behave in your analysis. Moving on from material nonlinearities to geometric nonlinearities, we need to talk about geometric transformation. So the geometric transformation in OpenSees, it's something that constructs the coordinate transformation between the basic or natural system of the element to the global coordinate system. There's one argument for each of these commands whenever you use one, if you type it down in your TCO scripts or if you put it in through the elements that you choose in STKO. I don't know if you guys remember this, but whenever you use OpenSees through like your TCO scripts without using STKO, you have to type down the geometric transformation command, let's say, without having to do it at the same time that you define your element. So it's something that it's separated from it. But we decided to include it in the element definition inside STKO. So you have to define the geometric transformation for each type of element that you assign in your model. Naturally, for beam column elements, the difference between linear and nonlinear analysis lies in the geometric transformation alone, because there's no internal geometric nonlinearities. We're not going to talk today about the type of geometric nonlinearities that can occur into solids or into shells, because that exceeds, let's say, the scope of these classes. We talk about frame structure, so we are interested in beam column elements. So we have 3 options for geometric transformation: linear, pdelta, and corotational. We said that we need to move from the global coordinate system of our model to the natural coordinate system, or local or basic, or how you want to call it. So, and this is reference to our element specifically. So any element that we have in our model is oriented in a different way, and that element have a different natural coordinate system. What does this geometric transformation does? It has 2 specific jobs. It has a job to transform the global displacement to the natural coordinates, and then back the natural forces and stiffness to the global coordinates. Because how does it really work? OpenSees receives, provides to the element, global displacement from the nodes to which it's connected, because of course in finite element our results are at the nodes. Then this element sends the global displacement to the geometric transformation command. It's an object. It's an object that does this transformation. So it moves this global displacement from the coordinates system of the whole model to the natural coordinate system and gives them back to the element. The element calls the constitutive model that we have defined. So if we already input the material nonlinearity in our constitutive model, that will be taken into account. And the constitutive model yields, we can say yields, forces and stiffness in natural coordinates. The element gives back these forces and stiffness in natural coordinate to the geometric transformation, which transforms it again, this geometric transformation object, transforms them again into global coordinate systems, which are given back then to the analysis, let's say. And so they can be transferred to, for example, other elements connected to that one, or anyway, saved into the results. So this is, let's say, a bit of the cycle of the things that happen. The geometric transformation has to do these 2 specific, of course, transformation. Yeah, there's not another word to say that. So what does it change if we are using, for example, considering our element? What we do is we want to record the state of this element throughout our analysis. What is that can change of this kind of beam element? The length and the orientation, given that a specific set of forces is applied to it, or a specific set of prescribed displacement, or I don't know, it depends on the type of analysis that you're doing. The geometric transformation, if it is linear, the length and the orientation of our element is going to be the same throughout the whole analysis. So initial value will be used, and the transformation matrix will be constant because we don't have any parameters that change through the analysis. Then we have the other extreme. If we use a corotational geometric transformation, then not the initial values are used, but at each step of the analysis, current values of the length and of the orientation are used to actually compute force and stiffness displacement from force and stiffness results from the displacement given by the nodes. So let's say we have a complete beam element nonlinearity involving large displacement and rotation, but of course we negate finite strains because we said at the beginning in the beam element we don't have what we can see actually in solids. So that's something that it's anyway excluded from nonlinear geometrical analysis. And then we have a middle ground. We have a pdelta kind of transformation that includes only the second order or large delta effects. So it still uses the initial values, but it adds to them the possibility of having large displacements. So this second order effects makes it that the transformation matrix is not constant, and we're not using the same values throughout the whole analysis in terms of initial length and in original orientation. So what the type of command that we use, it's always the same for the three types of transformation. Here, transformation type changes, but what you can define, it's always the same. I don't know if you guys remember how the vector z is defined. I didn't add the slides from week 3 in which we talked about this. If you need, we can go over it again. Just for you to remember that if you're using corotational, you cannot use the joint offset in 3D because it's not been implemented in OpenSees. But what can you obtain by changing this kind of transformation? Like, for example, I have a small model that I can give to you in which I made, I applied a very large load horizontally to this small frame structure. And without the geometric transformation and with the geometric transformation, you can see that there's a big difference in the results. So when we expect very large displacement or very large rotations in our model, then we can see that including the geometrical nonlinearities can give us much different results. Of course, this is like a, let's say, borderline condition. So we're not really at this point almost ever in our structures. But if we are doing, if we're pushing our structures a lot, for example, if we're doing a push down analysis of the self weight to see what's the ultimate resistance, then we need to take into account that the geometry of the structure changes throughout the analysis. So what I can, actually for today, I'm finished. What I can give you is the reference for this article on geometrical nonlinearities, which explains very well yes, this one, which explains very well what I tried to convey today on a mathematical level. Here you can see this is the type of transformation matrix that we have to use. Yeah, so this is the type of transformation matrix that we're using. We have a linear geometric transformation, and you see, no, sorry. This is the type of transformation that we're using if we have a linear transformation. Exactly, so the external geometric transformation matrix is 0 because we don't have additional components in the transformation. But instead, if you're using corotational, we have to take into account rotations. And we have to update the values of the initial. Yes, okay. And then if we instead we're using a pdelta transformation, you see we have to apply these delta effects inside of our transformation matrices but we're still using the initial value, so L0 and beta 0. And there's some examples here too for like modeling backlinks and modeling cantilever. Yeah, anyway, to add specific loading that increase over time and that you expect very large displacement or rotation to occur. And another reference I want to give you today, which can be very useful. I don't know if you guys ever explore Professor Scott's blog. There's one funny, he always have a very good irony when he talks about OpenSees topics. Hi, Hernan. Yeah, of course I can share the document. So, for example, there is this one about making sense out of concrete 02, and this is where he gives like default values for tensile strength, softening branch stiffness, etc. So, and you can also see the difference if you change the lambda value for the unloading ratio. So this is something that you can explore if you want to know more about these things. And of course, yeah, all the information I gave today, I can give you now the link if you are very eager to look at it. We were here. Yep. I will share it in the chat. And also the model that I showed with the difference between the linear and geometric. It's also gonna be shared online. So if you guys have any questions, we have time. We had a very short presentation today because it was theory and there's not much more to show than backbone curves and cyclic behavior. You don't need to have questions on the topics of today, of course. If you have questions on anything else, they are welcome. I don't know if you have questions on your models or if you are frustrated because I don't talk about the topics you're interested in. Anything you want to say, you're welcome to take the word.
So I think I have like a question for my model that I'm trying to do right now.
Yeah,
is that yeah, so I have like the question for the orient definition for zero length element. So
okay.
I kind of have a question how I should like define the vectors in the zero length command. I think I tried to read the OpenSees wiki, but I still didn't quite get it.
Okay, do you mean how to define the vector of the geometric transformation?
Oh no, like the zero length element command.
Okay, so let me share my screen. You're talking about length element OpenSees wiki. So you mean this kind of vector command?
Yeah, correct. Like because right now, I think I have like made a post on the OpenSees Facebook command, and I think Professor Scott has replied to me, and he suggests me to like read over the command manual. But I think like after reading it, I'm still a little bit confused because when you define zero length element, it's very important for how you want to tell OpenSees that when zero length element is in tension or in compression, and I think that's like it's based on how you define these two vectors, and I'm not quite sure how you should define the vectors.
So I think it works the same as the geometric transformation. I have to admit I've never had to write one myself because for us in STKO, you don't really have to do this manually, but there's a, let's say, a drop-down menu in which you choose the direction, and it's much more, let's say, straightforward, I think. So I guess your zero length elements, you can imagine it has something that has a finite length, even if it does not.
Mm-hmm.
And then with that, let's say, directionality, you define this kind of vector. So you say, I want my vector to go in that direction. And I guess this is the same as the geometric transformation. So let me just take that slide I was talking about that I did not reshare in this presentation because I thought it was not, I think it was with here. Yep. Is the geometric transformation command very clear to you or not?
I think the part I understand is that
Sorry.
I think the part I understand is that you define the local x-axis under global coordinate. That part I understand.
Okay.
Yeah.
But then, so is it in this one? No. No. Yes. Okay. So let's say that this is your zero length and it's not a beam column like here.
Mm-hmm.
When you want to say how this system has to move from local to global, you define a vector that it's in your hypothetical x theta plane, because you're with the x-axis, you're just saying what's the directionality of the first characteristic axis, but you're not saying how the section of the hypothetical element will have to adjust around that axis. Okay, because you could be oriented in any of the directions. Of course, when you're in 2D or 3D, this is most it's constrained by the fact that you are in 2D and 3D. But in 1D, that's not the case. So you have to define a vector that it's in your on your hypothetical. Have to be it can be any vector, just should not be aligned with X. And then from this value, you should define Y and Z with this kind of operation by doing the dot product with the norm of the X vector and the one opposite of the Y vector that you predefined before. Don't know if this makes sense. Let's see if in this documentation refers to something like that. Vector in global defining the YP vector. Exactly. This is the same, but for the YP plane. YXY plane. I don't know why I call this P. So I guess you have to hypothesize where is your Y going and put the coordinates of a vector that it's placed in that plane.
Mm-hmm.
Does that clarifies your problem or not?
Yeah.
Okay, so, and this can be any coordinates. It does not needs to be at all unity coordinate or anything. I'm sure it works the same for the zero length because it's like that in the geometric transformation.
And like one more question is that, so when I'm using the get element force command, okay, or when I use the get element force command from OpenSees, does it spit out the element force under local coordinate or global coordinate?
Coordinates. Oh, it's global coordinate.
Always global coordinate, and even the recorder is the same.
Okay. So my understanding that like results are always in global coordinates. I don't know if anybody else has any other information about it, but I think it's always coordinates. Let's check if it says something about it here. You didn't find any reference of it in the documentation, no? Lin? Kanjen Lin?
Yeah. Sorry, you broke up. You were breaking up a little bit.
Sorry, I meant like, did you find any reference? It does not say in the documentation if this type of output is in global or local coordinates?
So I think I did like some of the tests on my model, and and I got like a little bit confused of the output because yeah, I was like trying to get to the force from my zero length element.
Okay. Okay, I think it's in global coordinates, but I will check it out for you doing some tests and see if it's actually what I think it is so that we can be sure. Okay. So
Yeah.
you want to know about when you use get element results, right?
Yeah, get element force, and also like the recorder, output of the recorder from element.
So for the recorder, I'm quite sure in general.
Okay.
But then for the rest, I will have to check. We have another question. Thank you for your question. Can you tell me how to pronounce your name?
I'm sorry, you broke up a little bit.
Tell me how to pronounce your name correctly.
Oh, Kanjen.
Kanjen. Okay.
Yeah. Thank you.
So Aguzan is asking me, I couldn't quite catch the difference between corotational and pdelta in geometric transformation type. Okay, so the difference is that in corotational, you always use initial values in terms of geometrical characteristic of your structure. So if you are, I don't know, you're having a cable which is in tension, and that cable section kind of reduces under tension, you're anyway using the initial diameter, okay? Or you're using the initial, you're anyway using the initial diameter or the initial length or the initial orientation of the cable, if there is not just tension or something else. But then in pdelta, you actually add some, let's say they're called pdelta effects in the sense that there's additional effects in terms of the large displacement or large deformation that can happen. So there's kind of, I think there's kind of a threshold over which if there is a specific very large deformation or rotation, displacement or rotation, that effect is added into the computation. But the geometric characteristics are kept to be the initial ones. So if you actually are expecting very, very big effects of only very big effects, you don't want to capture anything else, you can use pdelta, but corotational is much more complete because it updates all the time. It updates all the time the value of all the geometrical characteristic of your structure. Does that clarify the difference for you? You recommend the corotational or not when we have large deformation in a solid body? You always ask me about solid structure interaction. I need to study more to answer to you. Because I'm not really expert in solid structure interaction. I need to study more for making you a course about it, a class about it. But I guess, did you check the pile solid structure interaction? Does Massimo uses corotational for his solid elements? Yes, so if he does it, you should use it. Take it for granted that it's right. Great. You're welcome. Thank you for your question. So if anybody else has anything else to ask, I don't know if Emilio is the Emilio from Salerno that I know of, or is some other Emilio. Or he doesn't want to show himself. No problem. So just for your information, as always, our material will be uploaded here for week 13 by tomorrow morning. you will be able to download the presentation and the example file from the frame structure. I wanted to create a little bit a utility for you to set up default parameters for this kind of materials that I created, but for now I didn't have time. Anyway, if you want to see what the backbone is supposed to look like, just input the same parameter that you see here in the presentation. I know it's not the fastest way, but I mean, it's something that you can reference to if you are actually looking for how to model this kind of material models, this constitutive behavior. And for geometric transformation, please review week 4 presentation as it was asked before. And it's, I mean, this is a quite difficult concept to grasp at the beginning, and it can be useful for other type of modeling, like for example, zero length. So just like try to actually fix this in your head, and also make some attempts even in one thing you can do really easily is to model something in STKO, extract with an MCO recorder your results, and then see them in STKO. So you can watch what you're actually modeling. And for example, you will be able to see section orientation if you modeled it in the right direction where you wanted it or not. So I think you guys, you 9 guys today don't have many questions, so I think we can wrap it up. If you have anything to ask, please do use our forum. And I will try to look at OpenSees Facebook too, so that I can check out other questions too. Thank you for participating. Thank you, Oguzhan, for participating, and thanks everybody. I'll see you next week, I hope. Maybe Larissa will come back. Enjoy your week. Bye.